All right, so now let's look at the idea of dominance. And the idea of dominance just has to do with the fact that some functions grow larger faster than other functions. And when you're dealing with like a product or a sum of two functions, the dominant function is going to be what the sum or product looks like over the long term. So um, so if you have two functions, let's look at, for example, e to the x and x. Okay, so we have two functions, and both of them go to infinity, right? As x goes to infinity, they both grow without bound as x goes to infinity. But you know, if you've ever graphed either one of these functions, obviously e to the x grows much faster than just the linear function x. So we say that the exponential function dominates the x function. All right, and so one way that we can test for dominance is by looking at the limit of the ratio of the functions. Of the functions. So we would try to put the bigger one on the bottom, when we would expect to be dominant on the bottom, right? And then if the limit of the, as x goes to infinity, of f of x over g of x goes to 0, then that g of x is indeed dominant, right? Because it grew much faster than the numerator, and so so it became larger and larger and larger, so the limit became smaller and smaller and smaller because it's in the denominator. And so that's one way that we can test for dominance, is just by looking at the limit of the ratio of two functions. So let's go on to example 7 and look at how we can apply this. So here's the example. We want to check to see if f of x equals x to some power p, for a positive power, so p is greater than 0, dominates the natural log function. Okay, we want to check that exponential power function dominates the natural log as x goes to infinity. So what we want to look at is the limit, right? So we're kind of expecting the power function to dominate, which, if you've looked at, if you could graph a few of these and see that, yeah, it looks like the power function is dominant. If we graphed x squared versus natural log of x, then it looks like x squared is always above natural log of x. This is a little bit different because we're generalizing p. We're just saying p is any positive number. So does it work for all power functions? Do all power functions where p is a positive number, do all power functions dominate the natural log? I mean, like x squared is a power, sorry, x to the 1/2 is a power function. So that's the square root of x, right? Does it also dominate natural log of x in the long run? What about x to the 0.1 or 0.01 or 0.0001? Is there like a power that eventually does not dominate natural log of x? So we're trying to answer those kinds of questions with this problem. So we're going to take the natural log of x and divide it by this power function that we're expecting to be dominant. And we know that this is an indeterminate form, right? Because they both grow without bound as x goes to infinity. They both go to infinity. So, and so we have this indeterminate form, and we can apply L'Hopital's rule to it. So if we take the derivative of the top and the derivative of the bottom, so the derivative of the top, derivative of natural log, is just 1 over x. It's kind of a funny looking 1, but oh well. And the derivative of the bottom is p x to the p minus 1. All right, now we can rearrange that. This is the same thing as the limit as x approaches infinity of 1 over p x to the p. All right, well, the natural log just totally went away. And you can see that if we have 1 over p x to the p, that is going to go to 0. So that tells us that x to the p dominates the natural log function for all p greater than 0. Which isn't surprising for, like a p-value of 2 or 3 or 4, but it is sort of surprising for really small values of p, like 0.000001. Eventually, that is going to dominate the natural log function. So it doesn't matter what p-value we choose. As long as it's positive, it's going to dominate the natural log function. It's just kind of an interesting result. So, all right. Another interesting result is in example 8, so I will see you in the next video.